Welcome to One Chemistry. Always try to do your best. Now let us see about 100 conversion in organic chemistry. We are seeing it as episodes. This is the episode number 91. If you didn't watch previous episodes, I encourage you to go and see. Here we solve 5 problems step by step. Stay tuned. Let us see the question number 1. The starting metal contained the cyclohexane, which contain one alkene, which is the ester of the acid group, which is above the plane. You are using the LDA and TMS chloride. You are using heat and hydrolysis. Here 4 products are given. The 4 products are differ in the stereochemistry of the connected bond, which can be carbon or oxygen or new 5-member ring with 6-member ring is formed. So here discuss the possibility of new ring closure or the switching of the carbonyl group. The carbonyl group switched from first to third, or the complete twisting of the ester to the alkyl substitution. From the question to product you might confuse where is the reaction center, and definitely rearrangement occurred here. The answer is D. Let us see how. The starting metal you have ester group which has one methyl group in alpha position. It has alpha hydrogen. You are using the LDA, which is a bulky base which abstract the proton. You have anion formation. Practically you can say enolate formation. To stabilize the enol form you are using TMS chloride. Silicon oxygen bond is stable, hence it stabilizes the enol form. So you have OTMS. Then you have alkene. So you have 2 alkene which is nearly to the terminal 6-member relation. So we bring both the groups nearby. So it's a kind of 6-member relationship, 6-member ring formation. Hence 3,3 sigma-tropic rearrangement is possible because we are using the thermal condition. So if you choose new 3,3 bond is formed, 1,1 bond will break. So double bond switches, you have the ester attached with TMS. Next step you are hydrolyzing, the TMS group will be removed. You have final acid there, which is D. Here you have to learn 2 important things. One is TMS chloride stabilize the enol form because silicon oxygen bond is higher, so always enol form will be there, no switching of ketone form. Second thing is sigma-tropic rearrangement. If you have 2 alkene which is in the 1,6 position, you might think of the rearrangement which is sigma-tropic rearrangement in 3,3 form. Here one important thing you should notice, since the reaction is concerted, the oxygen above the plane means product also above the plane. So in the concerted mechanism, stereochemistry will be retained. Then in the question number 2, the starting metal you have bridged system which contain the alkene in the 6-member ring. You have the bromine and NaOH one end and hydrogen peroxide and acetic acid in the other end. So the P and Q products are in the question, you have to identify. The answer is very simple, where the epoxidation is occur. Either it is above the plane or below the plane, or both will form above the plane or both will form below the plane. So from the question to product you might guess selective epoxidation definitely occur. Our role is to find the selectivity. The answer is A. Let us see how. Let us see the P condition first. The starting metal is alkene, you are using the peroxide. So peroxide always try to form the epoxide. So where the epoxide will form, endo or exo. Actually the exo will be favorable because it's sterically less hinted or less crowded. So final product will be above the plane, which is clearly B. Let us see the second and interesting condition. Instead of peroxide you are using the bromine. So bromine also facing the same less hindered bromine form above the plane. Next step you are using the base. Base attack from the below. Why? Because it follow through SN2 mechanism, so the attack is below. Next step you are using the base again. Base abstract the proton and O- attack the bromine there. So new epoxy ring is formed. So what is interesting here? Because O is below the plane, hence epoxide also below the plane there. So P is above the plane, Q is below the plane. Here you have to learn 2 important things. One is always epoxidation occur at the less hindered position, or you can say exo position. Second thing is opening mechanism of brominium ion. It's a kind of SN2 mechanism. So the attack is from the back side. So trans OH attacks. Here you have below the plane epoxide formation. Then the question number 3. The starting metal you are using conjugated ketone which have 1 methyl. You are using lithium in liquid ammonia and tertiary butyl alcohol. They ask you to find the product. So the products are mostly what happened to the double bond. Whether the double bond is reduced by ammonia or amine formation or tertiary butoxide substitution or just elimination of double bond or the creation of conjugation. The answer is C. Let us see how. The starting metal you have conjugated ketone. You are using lithium and liquid ammonia. It's a surplus electron donor. So it supplies the electron there. So what is interesting here? Because the addition is the 4th position. Because it's a thermodynamically stable form. Hence the addition is on 4th position, not on the carbonyl carbon. So the attack is there. The electron donation happened. You have radical as well as anion. Since you are supplying electron, the anion and radical occurred in the same system. Second step, you are adding H+. So H+ quench the anion, you have hydrogen addition. Then still the radical is there. Radical is very much unreactive, it has to be quenched. So lithium has C of electron, so the excess of electron again attack the radical, it form anion again. So anion again quenched by hydrogen there. So you have product C. Here you have to learn 2 important things. One is lithium and liquid ammonia. It's a reducing agent but selectively reduce the double bond here. The reason is thermodynamical stability. Second thing is the radical quenching. The all reaction driven by radical quenching and charge quenching. So if you have charge or radical, you have to always find the way to quench the radical. Then the question number 4. The starting metal you have aromatic system with amine and acid. You are using sodium nitrate and HCl. Next step you are using the diene with methyl group. They ask you to find the products here. The products are mostly fused ring system. It's kind of naphthalene system. What happened to really COH? The COH form a lactone kind of architecture. COH and the aromatic ring or aliphatic ring are in the side chain. So from the reactant to product you might guess the ring closure definitely occur. The amine and acid in the same system with the NaNO2 definitely special intermediate formation. The answer is B. Let us see how. The starting metal you have amine, you are using NaNO2 and HCl. It's a kind of diacetization. Amine become N2Cl there. It's a salt. Then you have carboxylic acid and N2. N2 is a good leaving group. Carboxylic acid also there. So there is a formation of benzene. Because CO2, N2 are very good leaving groups. Because the multiple bonds are there. That's why benzene is formed. Benzene is double bond in the benzene ring. Next step you are using conjugated diene. So obviously 4+2 cycle addition will be there. New 6-member ring will be established with double bond. So the answer is clearly B. Here you have to learn 2 important things. One is amine and acid in the same system which is in the ortho form, meaning you can have the possibility of benzene. Second thing is benzene can undergo 4+2 cycle addition like any other alkene. Then the question number 5. The starting metal is benzaldehyde and you have the dithiol there. You are using BF3 and ETO. Next step you are using LDO and the allyl bromide. The next step you are using the ranny nickel. Here 4 choices are given. 4 choices definitely you have new CC bond and alkene attached different way. Whether alkene attached with OET or methyl or new CO is established there or not. From the reactant to product you might guess reagents are playing important role and it dictates the conversion. The answer is B. Let us see how. The starting metal you have ketone and you have dithiol there. Dithiol protect the ketone by just SS bond formation. Then you have new 2 CS bond formation with 1 proton there. The proton will be active because of electronegativity difference. You can pull out the proton easily. So you are using LDA. Proton abstraction will be there. Anion is formed. So you have anion formation. Next step you are using allyl bromide. Bromine is a very good leaving group. You are attacking with anion. So new CC bond formation will be there and you have thiol. Next step you are using ranny nickel. Ranny nickel only cleave the CS bond there. You have just hydrogenation there. So you have product B. Here you have to learn 2 important things. One is converting CO bond into CH2 through the multiple ways. Because the nucleophilic attack of allyl group is there, then it convert to CH2. If you directly attack it, you will not get the desired product because reduction is not effective because of alkene there. Second thing is thiol group. Thiol group product the ketone and it allows the continuation of further progress with different reagents. That's all from this episode. I hope it was easy. Thanks for watching. If you have any suggestion, comment below. Stay tuned for next episode.